Okay, we are recording now. And I hope you had a good off day last Wednesday. I guess we are not having spring break this year, so we have these off days, but Wednesday, Thursday, Friday are the off days. So we are done with the off day for this course. Getting back to where we are in the course. First of all, MP1, I hope you're working on it. Homework 2 is due end of this week. I would say the homework 2 is very aligned with material that we are covering right now. So get started on homework 2. In fact, that would help you understand what we are doing. I hope things that we've been talking about in DSP thus far have been clear, although things are getting a little bit involved, but I'm hoping that it's still reasonable for you. Let me quickly do one thing, 1 second. Yeah. Oops, sorry. This is not the right one. This is the right one. Oops. Gotcha. Yeah. The goal today is to finish up signal processing. And then from next class onwards, we start with some applications. And again, we might come back to a little bit of math as and when necessary. We will have to. But I think we did quite a bit of foundational math thus far, and probably we need a break. And we'll talk about applications. So any questions thus far? Any comments on what, any changes we need to make? Are you getting bored of math? Is this useful? Is this too slow, too fast? Give me some sense of any questions. Okay, I would take that as you are following. Did we run over last week's material or just started? No, we have not revised last week's material. We just started right now, so yes. If some of these things have bothered you, please do spend some time in getting these concepts right. The homework should definitely help. And the reason I say this is because from linear algebra and signal processing, I'm taking out material which is most useful in various things you'll do in this course and maybe many other courses. And throughout your career, I think these are foundational. So please try to spend time and if there's something that bugs you, bothers you, don't let it go thinking I'll look at it later, because you'll never get a chance. Life will keep happening, right? So just drill down on it, because the only thing I would say is getting this right is like a key to opening many doors downstream. Okay, good. So let's jump in with that. I am hoping that things were clear from last week. The high level message was, if we want to look at the FFT of signal like cos 2 pi ft, right? Where in the digital domain, it becomes cos 2 pi f nts, n being that sample number. We said that, look, for a real signal, the FFT will have to have two frequency components. And why is that? We said whenever we are in doubt, we are going to step back and say any signal can be made up of rotations, right? Rotations are like Lego blocks, where these rotations are rotating at 1 full cycle per n time units, 2 cycle per n time units, 3 cycle per n time units, and so on. These are our Lego blocks. And now if someone says, what is the FFT of cos 2 pi FNTS? It's like saying, can you build cos 2 pi FNTS using the rotational Lego blocks that you have, right? So, and then we said, look, we have this Lego block which is rotating. And what we really want is that stick's x-axis projection. So this is cos 0, which is 1 in the real axis. This stick rotates theta, but its projection is cos theta. That is what we want. Then the stick rotates to cos 2 theta. The projection is cos 2 theta. That is what we want. And if we take cos 0, cos theta, cos 2 theta, and so on, that will exactly be the signal that we are trying to reconstruct, right? So we said, good, the rotation actually gives us what we want, but it gives us too much because it also gives us this sine component, right? When the stick is rotating, and that sine component is along the complex axis, the j axis, because remember we said initially, we just made up j as the 90-degree rotation. So we said, look, if we want only these cos theta values, we need to somehow combine Lego blocks such that the combination of those Lego blocks would cancel out the j-axis values and only the x-axis projections would remain. How can you do that? Because if we can do that, we are done. We have showed how to combine these rotational Lego blocks to actually make cos 2 pi f and ts. Right? And there we said the way we would do it is use another rotational block which would rotate in the opposite direction, right? If this rotates in the forward direction, then we want another one which would rotate in the opposite direction so that this y-axis projection and this y-axis projection would cancel off, right? But then we don't have any rotational block that rotates in the opposite direction. Would you agree? All the rotational blocks that we have seen are all rotating in the counterclockwise direction, just with increasing speed. Well, one observation we made is super high speed is nothing but rotating in the opposite direction, right? So we take this stick at some speed f, and we take another stick at some speed, or let's say this is at speed 1, we take another stick which is at speed n minus 1, which is like really, really fast, right? And we add these two. So this is like the second step of speed 1, and this will be the second step of speed n minus 1. Hey, they'll all cancel out the y-axis projections, and together you will only get cos theta out. Of course, because you're adding two sticks, both of them are length 1, we need to kind of make both of them multiplied by half by a scalar so that the net outcome is cos 1 times cos 0, 1 times cos theta, 1 times cos 2 theta. So we multiply those by half. As a result, when we look at the FFT spectrum for cos theta, we really have one frequency at f1. Let's say this one is this cos 2 pi f1 NTS. One frequency at magnitude of half at f1 and magnitude of half at fn minus 1. This is essentially saying, take your Lego block of frequency rotation f1, make that Lego block, make that stick half, take another Lego block frequency fn minus 1, which is the fast one, bring that to half, add it. Voila, you would get cos 2 pi f1 NTS, right? At every step of that rotation, which is time, if you add them, they will together always cancel off the complex axis, and you will be left with cos 2 pi f and ts. And that means that this is the Fourier transform of cos 2 pi f1 and ts. If you get this clear, you are ahead of many, many people who think of FFT with only like a equation, as opposed to really seeing what is going on underneath, right? And this is exactly why real signals will always have symmetric frequencies. They have to have, right? Because you have to cancel off the complex values of these rotations. So they have to have these positive rotation and the negative rotation, but the negative rotation is nothing but fast rotation. Very good. And then we looked at sine and we said, look, sine is a little bit different. And we said for sine, the sticks need to start at a different angle. The first stick needs to start at 90 degrees, negative 90 degrees. The second stick needs to start at positive 90 degrees. And then if you take the time steps of the stick's rotation, they're all going to rotate counterclockwise, all of them. But you make their starting positions different. As a result, you will see that you actually get sine 0, sine theta, sine 2 theta, and so on. Okay. Again, so if you look at sine's FFT, it will again be symmetric because it's a real signal, right? Sine is a real signal. Sine 0, sine theta, sine 2 theta, and so on. It's a real signal. So it will be symmetric. But the phase of the two building blocks, remember we said, what is phase? I think this picture was kind of trying to tell you that phase is nothing but you have these Lego blocks and you add them together, you'll get this structure. This was in some sense cos, where you added these two Lego blocks without having to move them. But this was in some sense sine, because now you had to move this Lego block and add it to this so that you create sine, right? So this is really the phase. Right? Again, this is an analogy, but the point is that these rotational blocks that you have, 1 degree of freedom is which rotational blocks you choose. That tells you which frequency makes up that block, that design, right? The other degree of freedom that you have is once you choose a rotational block, you can even make it start. You can make that stick start at a different angle, which is equivalent to saying I have bunch of building blocks and I can choose which building blocks I need to make this shape. But I can also choose some shift of this building block to make that shape. It's not that if I choose the building block, I have to start all the building block at the same location. Right? So this shift that you're doing to the building block to make this shape is the same as the shift that you're doing to the rotation to make the signal that you are asked to, right? And that exactly is phase. Very good. Okay. So we finished sine, and with that, we'll continue with today's lecture. Any questions? Very good.
I kind of have a question.
Okay, great. Go ahead.
You said you always have like two frequencies to cancel out the imaginary part.
For real signals. For real signals.
It's not always true, is it?
For real signals, always true.
What if you had for sine, it's just like sine theta and then sine 2 theta, and theta is like equal to, I don't know, like 180 or...
Right. Will the value have complex values? Will sine have any complex values?
What if it just alternates between 0 and 1? In terms of like the amplitude, and there's no what is it called? Imaginary component.
Right. So sine will never have an imaginary component, right?
For very certain values, right?
For?
For a certain value, like maybe like 0 or 180 or...
No, but for what value will sine theta, for what value of theta will sine theta have imaginary values?
Everything except for
it's hard. If you plot a sine signal, let's say this is x-axis, right? And you go from minus infinity to plus infinity.
Yeah.
And you plot a sine value, sine signal. No, sorry. No, that's wrong, right? This way. It'll always alternate between -1 and 1.
Yeah.
It'll never have an imaginary value. Right?
Yes.
And rotations have always these imaginary values because these are sticks that are rotating in this 2D plane, and the y-axis of the 2D plane is the complex value, j.
Yeah.
Right? So anytime you try to make this real signal with an imaginary, with a rotation that has imaginary values, right? You have to cancel off the imaginary values.
Okay.
Right? So you always will have to have two symmetric frequency components if it's a real signal. Very good. Okay, so let's start. Okay, so now let me ask this question. The first topic we'll talk about today is beware of incomplete cycles. Okay, let's say what it means. Imagine you have this signal, which is the shape of a cos. Okay, and you take n-1 samples, and it is exactly one full cycle of a cos. And then again, after this, it's like this is the cos signal. Okay, what is the FFT of this signal? Suppose I try to write that FFT in like only the magnitude, let's say. Let's say this frequency is F1. So what should you see as the FFT? Guys, this is trivial question, easy question.
There should be kind of like a stick at F1 and then another stick at
Fn minus 1, let's say.
N-1, yeah.
Right? This is at half, this is at half. You all agree? Right? This is what we talked about. Very good. Suppose this is another signal and this one is F2, right? What should you see? You should see F2, Fn minus 2, right? And these are both half. I'm saying nothing new. I'm saying repeating the same thing with a different frequency, right? The F1 was here. F1 was here. This is F2. Fn minus 1 was here. This is Fn minus 2. Right? You have this is a higher frequency. You see that this is a higher frequency than this, right? Right? So the signals have shifted nearer. Very good. Now, what is the FFT magnitude? This is the FFT magnitude spectrum. What is the phase? The phase is all 0 because this is cos. Right? Very good. Now, what is the FFT magnitude spectrum of this signal? And this signal is almost the same as this signal, except that instead of this last part, this is 0. So this is the same as the previous signal, except this part is all 0. What is the FFT of? The question is the FFT of this signal the same as the FFT of this signal? The only difference is this has incomplete, in the last portions, there is 0. So the frequency of the signal is the same as F2, but the last part all has zeros. Will this FFT and this FFT be the same?
I'm just going to say no.
No. No. Okay. I think from my voice, from my tone, it's clear. No. Tell me why. Just in English language, tell me why. Yeah.
I mean, I'm not sure I remember, but I'm just going to take a wild guess and say that since it doesn't contain all of F2, it can be, but it does contain all of the F1. So it might be that the magnitude spectrum could be what we had for the first one.
Oh, you're saying this one could be the same as this one?
Or no, the same. I mean, it contains that, right? But it doesn't contain all of F2, so it can't be. I know for a fact it can't be F2. Or I mean, right?
I see. You're saying it could contain F1, but why does it contain F1? Because look at the frequency of this signal. How fast is this signal moving? This is not moving like F1, right?
Yeah, that's true.
That's true, right?
Yeah.
So someone tell me, I think we all agree that this frequency is not going to be the same as this frequency. The question is why? Can't I say that, hey, this is made up of F2 frequency. Yeah, it's partial, right? It does not have the full symbol, full completion of the cycle. but it has F2. Why can't I make this signal with an F2 rotation?
Is it because it has to handle this case of the zeros at the end?
Exactly. If you use the building blocks of F2 and Fn minus 2, you will get the first part beautifully. Right? But those two building blocks, the last few time steps of those two building blocks will give you this. Will not give you this. Right? And once you've picked those two rotations, you cannot say, okay, I'll use these two rotations until some n minus k. Let's say this is n minus k. This is time, by the way, right? Right? This is time. So you cannot say, I'll use these two rotations until n minus kth sample, and then I will not use that. You cannot say that, right? If you've picked those two rotations, all you can do is pick which rotations you want and change their starting phases. That's all you can do. After that, they will rotate and they'll create the signal for you. You cannot say, I want that for part of the time and not for the other part, right? Once you've taken a course in a semester, you cannot say, I'll take half of this course and half of that course, right? You have to just, once the deadline has passed, you have to just be in that course for the rest of it. Okay? So what that means is, you can think of this signal as nothing but I made a mistake here. Yeah, you can think of this signal as this original x2 times another signal, which is a rectangular signal Do you agree? If you multiply this signal and this signal, this is a signal which has only ones all the way till n minus k and then has zeros. If you multiply these two signals, it will be this signal. Do you agree? Right? Let me just label that as 1. So that means the DFT of this signal, is the same as the DFT of this signal, right? And now, clearly, because this signal is involved in this DFT multiplied, therefore, we can clearly say that DFT of x3 is not equal to DFT of x2, where this is x3 with the last trailing zeros. Right? It is not the DFT of x2, since the DFT of this rectangular pulse or rectangular pulse train influences the results. And this is where it will turn out, if you want to create this x3 signal, it will become a composition of many frequencies. You will need many rotations so that the initial ones look like a cos, but at the end, they all cancel each other out. It'll turn out that if you take the FFT of this, there'll be many, many frequencies, all of them added up together to give you this whole signal. Okay, very good. Now a similar question. Now look at X4. Okay, so this X4 signal is somewhat similar to X1, but X1 completes one cycle, but X4 completes 1.5 cycles. Because if you finish this signal over here, that is one cycle, but you have this, 1.25 cycle, right? Again, over here, DFT of x4 is not the same as DFT of x2, sorry, x1. X2 or not the same as x1 also. And the answer is no, it is not. Right? Because one and a quarter cycles, 1.25 cos cycles cannot be made up by integer number of rotations. Does that make sense? Right? Because if you remember for x1, after those full rotations, you are getting a full cycle of cos. If there is 1.25 cycle, or even one plus a little bit of that cos cycle, if it's not exactly a cycle of cos, then the FFT becomes very different. Okay? And oftentimes, if you model these things, the FFT of this signal is what is called a sinc function. And that sinc, we are not going to get into the sincs, but because of that sinc, now you start getting many frequencies which are needed to make up signals like this or like signals like this. Okay, very good. So again, remember yeah, go ahead, Utkarsh.
Could you scroll up a little bit?
Sure.
When you say the DFT of x3 and x2 are not equal, since the DFT influences results, what do you mean by that last statement?
Oh, because this x3, right, is essentially x2 times a rectangular signal, right? This is a rectangle, right? So because this signal, so in some sense, DFT of this full signal cannot be only the DFT of this, because this guy is going to influence that DFT.
Okay.
Right. So that's what I mean. And what I'm not getting into detail is the DFT of this rectangular signal is a sinc function, and that sinc function is going to influence this signal, the DFT of this whole signal.
Okay, so in this and in the X4, are you showing like, is this an actual cosine signal, or are you trying to show that it looks like it, but it's not?
This is a cosine signal.
Okay, so you're saying this is...
I'm saying is,
order cosine?
Remember, this is a cosine signal, right?
Mm-hmm.
I'm saying in those same n-1 samples, this is another cosine signal, but it has a higher frequency or a lower frequency, guys? Someone?
Higher.
Higher.
X4 is a higher frequency, right? Because it completes 1.25 cycle in those same n-1 samples compared to this.
Mm-hmm. Okay.
Good. Okay. So another way to just look at this same thing is that, look, remember that we have this frequency basis, right? These are our rotational building blocks. And any signal is this green vector. Remember our first conversation, right? If this green vector happens to be a cos signal, let's say cos F1. And when I say cos F1, it's a short for cos 2 pi F1 NTS, right? Let's say it's a cos F1. What does that mean? That means if you take that green signal, the projection of the green signal on F0 will be 0. That green signal lies in the two-dimensional plane of Fn-1 and F1. That green signal lies in this 2D plane. hey, this should plug all the holes and this should bring everything together. The green signal, which is cos F1, essentially has projections on F1 and Fn minus 1. That's why cos F1 only has those two as frequency values. Others are all 0. Right? That means this green signal cos F1 must lie on the 2D surface composed of F1 vector and Fn minus 1 vector. Right? Of course, this is happening in very high dimensional space. So there is a 2D hyperplane over there. Right? But the moment you take this signal, this is not cos F1. This signal is not cos F1. This is cos F1 plus epsilon. Right? Which means that vector is no longer in that 2D plane. It becomes a little bit different. And now that vector will have projections on all the other frequency axes. Right? So it's actually very clean, right? Signal is a vector. When it's cos, it exactly lies on the 2D surface. When it becomes something cos plus something, it's in another vector, and that vector, whatever the projections are on F0, F1, F2, F3, F4, all the way till Fn minus 1, that is the FFT of that signal. Very good. So think of this as correlation or projection of the signal on the frequency basis. You understand projection? Correlation is a kind of a projection, right? Even if you don't understand correlation at this point, don't worry about it at all. Just think of it as FFT is nothing but you take the signal as a vector and you project it on every dimension of every frequency dimension. The frequency dimensions form a basis, and you take the values of each of them, and that's your answer. Quick question to you guys. If this is cos F1, what is this value? Half. What is this value? Also half. What is this value?
0.
This value?
0.
You guys are ready. Okay? Very good. Okay, so now real voice signal. Suppose I record my voice, you record my voice. This is what you're going to do in MPs now, later in the homework, etc. You think your voice has this beautiful property that everything is going to be nice, cos, full cycles? It's not going to be. Right? Your voice is going to be things like this. You say, Alexa, and then you pause. It's all zeros. Right? You say Siri, right? It's going to be, your voice is going to be all kind of crookedy stuff. Right? And so then when you take your FFT, don't expect your FFT to be beautiful as this. Right? In fact, this is what your FFT is going to look like. Okay? Let's look at this. So this is a real spectrogram. This is a real voice spectrogram. Okay, this is the voice signal. That's time. Let me write it. Oh, I already wrote this as time domain signal. Hello, how are you? Right? Now you take an FFT, but what you do is you take a window. You take a window, you take the FFT, and then you shift the window. You take the FFT, then you shift the window. You take the FFT, you shift the window. You take the FFT, and you keep doing that. Okay, so you have a sliding window, and for every window, maybe there are 1,000 points in that window. That's an n point FFT. You keep taking that. So this graph is called a spectrogram. On the x-axis is time, and the y-axis is frequency. Okay, time means this is time 1, this is time 2, this is time 3. Okay, let me make it clear. This is time 1, This is time 2. This is time 3. This is time 4 because they are overlapping. Okay. And frequency means for that particular first time window, actually, let me draw this. So this, take any, okay, let me draw this. This shows the variations. This shows the various frequency components at that time instant, at that time window. So this is S for Siri or A for Alexa. Okay. So that, let's say Alexa, A will have these strongly these frequencies, and then these other frequencies will be low. Red means strong. Blue and green means low. Right? So they'll have strong frequencies at, like, this is a strong one, right? So this is around 300. Right? So 300 hertz will have a strong value. Okay? And there'll be some 600, 900, and so on. In fact, look at this. Do you see these stripes? You see there's a striping behavior, right? Human voice has what are called harmonics. So you have a base frequency, meaning when I say hello, that her has a base frequency, let's say 200. And the other frequencies that my voice will generate are 400, 600, 800, 1000, and so forth. It'll be like integer multiples of that base frequency. A lady would have a higher base frequency, right? That would be a higher frequency. And if that is like 350, she's going to generate 350, 700, 1050, so on. And as you go higher, the energy will be less and less in those frequencies. Okay? So this is an example where you're taking a time sample and you're looking at what are the frequency components in that time sample. Of course, as you move this window, as you move this window, the different frequencies will change. This is a pause in your speech, so you don't see too much of frequencies. Right? Again, a pause maybe in your speech. Right? But this is really in the center of your speech. Good. Now, in the other way, you can slice it the other way as well, which is you take a particular frequency, and now you can see how that specific frequency comes and goes over time. Right? So, for instance, this 1000 hertz, 1 kilohertz, is strong over here, Maybe it's saying Alexa, but it's saying, Alexa, how are you? And maybe how does not have right? So this kind of a thing is not there in how, right? How is more, right? It's more lower frequencies. Right? So this tells
Professor, can I ask a question?
Yes,
sorry.
Please. Yes.
Sorry, I didn't mean to interrupt you. We use a sliding window as opposed to one big window because we want to differentiate the frequencies at each time instant, right?
Correct, because frequencies are changing, right?
Right. Okay, thanks.
Good. Also, hey, the computation is also much larger if you take the whole signal and take an FFT.
That's true. It's faster with less points, right? Okay.
Exactly.
Okay.
Correct. Okay. So this is basically pulling the whole picture together. Okay. And this gets real because this is actually a voice signal. And I think in your homework, we ask you to basically take time windows and look at this frequency slice. Okay? So you're going to look at this slice and feel free to play with your, even if the homework doesn't say do many things, feel free. Once you have the code, feel free to play with it. Record your different voices, record a female's voice, record make your laptop say something like a synthetic voice and see how those frequencies change. Very good. Okay. Now we'll move on to the next thing, which is we'll talk about 3 properties of DFT, and you've already seen these. So now it should be kind of a revision. We should be revisiting stuff. So first property of DFT is that DFT is linear. What does that mean? It means if you take a signal, which is, let's say, your voice plus my voice. Okay. I take your time domain signal, your voice is time domain signal, my voice is time domain signal, and I add it up. Okay. Because DFT is linear, this should be DFT of Xn plus DFT of Yn. Okay. Which is nothing but Xm plus Ym. Right? We're writing M as frequency. Right? So guys, what is DFT of cos 2 pi f1 NTS plus cos 2 pi f2 NTS? Or sine 2 pi f2 NTS? Yeah, let's do that. Let's say this signal is Z. So what is the magnitude of Zm? And what is the phase of Zm? Quickly. F1, F2, Fn minus 2, Fn minus 1. Similarly, F1, F2, Fn minus 2. I've already given you half the answer. Now tell me.
Try the phase one.
Huh?
For that, and then for the cosine, and then want to just be F1 and then F1, or Fn minus F1.
Yeah.
Or yeah, Fn minus 1. And
yeah,
then for
you're right. You're right. It actually should be Fn minus F1, but we are doing some abuse of notation here. But
yeah. And then for the sine part, it should be at F2 and F2 minus or Fn minus 2.
Right.
And then for the phases, like, right. I mean, I think the cosine should both be up, but then the sine, first one should be down and the second one is up, or the other way around?
Cosine should be what?
I thought that for the phase, or the phase should be 0, right?
Yeah, right. All zeros. But what about the sine?
I thought one of them is supposed to go up, the other is supposed to go down.
So that's it.
Cool.
Right? You just take this one's FFT, you just take this one's FFT, you just add them up. That's it. If this was cos plus 2 sine 2 pi f2 NTS, what would happen? How would you change this?
The magnitudes won't be 1/2, they'll be 1, right? For sine, at least.
Sorry. Good. Glad you got that. So now the magnitude would be, this is half.
Is the first phase at F2, is it always negative, or can that be positive and the other one's negative?
No. That's what we did, right? Remember, we said that if the first one is not negative, and if you make this one positive and this one negative, it won't work.
Okay.
That is where I might try to trick you in the midterm. Okay. So this has to be that. And the phase does not change as a function of the amplitude. Agree? Because the size of the stick has nothing to do with its starting point. Okay. Very good. Okay, so this is linear. And because it's linear, it makes life much easier for inmate. Sorry, this is not going to work. Okay, let's leave it there. Okay, good. Second property, for real signals, DFT is symmetric. Okay. I want you to now pay attention. So when we said symmetric, we said, look, if let's say these are the components of the signal. Actually, let's make it like a triangle, just to be. So what should the symmetry look like? Where should this guy go? Where should I put this? Oops, sorry.
Is it to the right of the fs over 2?
It's just, okay. You're right. So I'll just write, it's at the right of fs over 2. Are you all with me? This and this are at the same height. Okay, let me make that at the same height. Are you all with me about symmetry? Right? If this guy was like this, then this guy would be like that. You all agree? Very good. So this is symmetry. For real signals, this is exactly what is going to happen. Okay. But now this is where I want you to pay attention. Let's copy this. We said that, actually, one second. Now we said that the fastest frequency actually makes the stick go backwards in the slowest way. Make sense? N minus 1 theta is basically the slowest frequency in the backward direction. Right? Now, in the backward direction, what would be the slowest frequency? Minus F1, right? If F1 is the slowest non-zero frequency, minus F1 would be the slowest non-zero frequency in the negative direction, in the opposite clockwise direction. You agree? So can I say that this is the same as this?
Yes.
Yes, very good. I wanted that, yes. Can I do this? So this I can move it here. Or it's this equivalent. This, where can I move? I can move it here. This I can move it here. Are you with me? So now, initially we had said that this is the bandwidth of the signal. Initially we had said this is the bandwidth of the signal. But we can now also say, look, this is the bandwidth of the signal. Right? So this is where people typically use the blue notation. So this is where we say minus fs by 2 to plus fs by 2. This is my bandwidth. Okay. And this is where the notion of negative frequency comes in, that, oh, my bandwidth actually goes from positive to negative. Actually, it's nothing, no big deal. My negative is essentially super positive, right? The faster of the positive, that actually has become negative, right? But you actually basically copy paste this part and you move it over here, and you basically copy this part and you move it and paste it here. Right? So I just to make sure that the notes are ready, notes are complete. Very high frequencies or very high speed / frequency is same as spinning in the negative clockwise direction, negative or clockwise direction. Guys, is this completely clear? Any issues?
Yeah, Professor. So the negative frequencies, are they shadows of higher frequencies, or are they frequencies that are not being like displayed on a graph at a time? Like, what exactly are they? Because we can still display those same ones in the positive direction, right?
Right, right. So all I'm saying is, if I can choose to write these frequencies, I can choose to draw these frequencies as these values.
Okay, so they're one and the same though, right?
They're the same, exactly the same.
Okay.
Right? It's like saying 5 is the same as minus minus 5. If you tell me which is right, I would say both are right.
Mm-hmm.
Minus of minus 5 and plus 5 is the same, right?
Yeah.
So all I'm saying is this is just another representation for this.
Okay.
This is just going clockwise. This is going anti-clockwise.
Yeah.
Perfect.
Because depending on the window we choose, and I mean, even though we were getting different shapes, they're essentially still the same, right?
Which shape?
I guess like the shape of the line we draw connecting those dots doesn't represent anything, does it?
Oh, it doesn't represent anything. I just, okay. Yeah. Yeah.
Okay.
Yeah. This shape doesn't represent anything.
Okay.
Okay. I just drew it to show that there's a symmetry here. Let me draw it with a different.
I got it.
This shape, this and this has to be mirror images. Right? The blue, this blue thing that I drew, right? They have to be mirror images, right? It has to be symmetric, right? Because this and this is symmetric. And because we have copied this and put it here, so this and this have to be symmetric. Hey, what's any issues there? Anything bugs you there? Nothing, right? Good. Anirudh, is that okay?
Yeah, no, that works.
Good.
Sorry, I was.
Sure. Okay. So you take frequencies in fs by 2, comma fs, which is this region, and move to the negative frequency axis. It's like the negative frequency sticks are going clockwise, that is negative theta, to cancel the complex part. Very good. Third and last property we'll talk about is that the DFT of a shifted signal is the original DFT with a phase shift. This is a little bit more involved. Imagine this is the digital signal we have, the black vertical lines. And let's say that we take a window of those samples, which is the green window. And this is a repeating signal. And we take a green window and we take an FFT of it. Let's call that XM. Okay. And now we take another blue window, which is a shifted version. And we call that signal X-N. Okay. Of course, the DFT of X-N will be X-M. These two are different DFTs. Okay. The property says that X-M is XM to the power. Okay, somehow I didn't write the property. Okay, let me just write this over here first. The property says that XM, X-M equals XM times e to the power j 2 pi by n m k. Okay, so it turns out that suppose I say, okay, how will you calculate X-M? right? X dash m is nothing but the FFT of the shifted signal. And it turns out X dash m is nothing but xm times e to the power j 2 pi by n mk, where k is the number of samples that you've shifted. This is k. Okay, this should become clear once we do the derivation. So let's shift x by k samples, and that gives you x dash n. So x dash n is nothing but xn plus k. Are you all with me? The first, the x dash 0 is nothing but x of k. X dash of 1 is nothing but x of k plus 1. Right? Very good. So x dash m is nothing but DFT of x of n plus k, right? Just take DFT on both sides. Okay. What is DFT? DFT is nothing but n equals 0 to n minus 1, capital N minus 1, x of n plus k, oops, times e to the power minus j 2 pi by n m n. Standard DFT formula. I'm just trying to compute a DFT for x of n plus k. Okay. But now I'm going to massage this a little bit. I'm going to write this as x of n plus k e to the power minus j 2 pi by n m times n plus k times e to the power j 2 pi by n m k. Tell me if that works out. Basically what I did was I wrote this n as n plus k minus k. Right? And this n plus k comes here. And this minus k, that minus and this minus becomes plus, and it becomes mk. Right? Simple. Very good. What is this? What is that?
Same thing as before.
Which is?
XM.
Correct. This is nothing but XM. Right? Don't get fooled by the fact that this n plus k and this n is 0. This n is saying, I'm going to count n minus 1 positions of the stick. Right? This xn plus k and mn plus k is like n positions of the stick. Just that the first value, instead of being xn, is xn plus k. So this is exactly xm. And this gets multiplied by e to the power j 2 pi by n mk. Right? Now, this 2 pi by j mk, this means a phase shift. Why does it mean a phase shift? Guys, remember when we took a stick and we were making it rotate by theta, 2 theta, 3 theta, that rotation was e to the power j0, e to the power j theta, e to the power j2 theta, so on, e to the power jn minus 1 theta. You remember that? This is the vector that embodies a rotation of one full cycle in n time units, right? So if I multiply this by e to the power j phi, what happens? This becomes, this becomes e to the power j phi. This becomes e to the power j theta plus phi. This becomes e to the power j 2 theta plus phi. You agree? So what is e to the power j phi? E to the power j phi is nothing but you take that stick and you start it from phi. Actually, I should draw it this way. I shouldn't draw it like, I should say, you start the stick from here. And then e to the power j theta plus phi is now the theta moves. So this angle is theta plus phi. You agree? So once you multiply this vector by this e to the power j phi, it's as if you've moved the whole vector, or you move the rotation, the starting point of the rotation by phi. Make sense? So what you're really doing in this case is you're taking the rotation vectors that are contained in xm, the FFT of xm, and you're basically taking each of those rotation building blocks and you're shifting it by some phi. Does that make sense? Okay.
Professor, could I ask you a question?
Please, please.
The xn, when we say like x of n plus k, the n plus k, like this k is just a generalized k that could be positive or negative, right? Because normally we think of a right shift as like minus k.
That's right.
Right.
That's right.
Okay, so this is just like generalized, general.
You can put that k as -5. Yeah.
Gotcha. Okay. Okay.
Perfect. Okay.
Hey, Professor, why is it negative j instead of j again?
Oh, because remember we wrote this as n plus k minus k, right?
Mm-hmm.
So if you take this n plus k, so that will be, because remember this is all minus j times that, right?
Yeah.
So n plus k would remain n plus k, and minus k and minus j would become plus j. Basically this minus and this minus would become plus.
Okay.
Hey, no. If it's not okay, it's fine to say it's not okay. It's very, I'll just quickly write the intermediate step over here. E to the power minus j 2 pi by n m times n plus k minus k.
No, I get that part. I'm just wondering why there was an j in the first place. Or is it only positive j when things are being shifted?
No, say that again. Say that again.
No, just because I think in the previous lecture you went over the definition and it showed negative j, right? Is that just like the textbook definition of it?
No. Negative j came from, we did F inverse.
Okay.
Remember, right? We were saying I times x in the time domain is f times x in the frequency domain.
Yeah.
Right? Or this, we can write that as m, right?
Mm-hmm.
And we said xm, therefore, is f inverse of xt.
Okay.
And this f inverse of an orthonormal matrix is nothing but f conjugate transpose. And this conjugate brought in that negative j.
Okay.
Because e to the power j theta's conjugate is e to the power minus j theta. And that is why in the FFT equation, we have minus.
Yeah, so the xn plus k is the xt part in technically in this case, right?
Say that again.
Is the x of like in like the square brackets of n, is that the xt part or no?
That's the xt part. Yeah.
Okay.
Yeah.
All right. Thanks.
It's in samples, right? So that's why it's n.
Yeah.
That's right.
I get it now. Thanks.
Good. Very good. Okay. So this is a phase shift. Okay. Now, this phase shift is proportional to k and to m as well. What does that mean? That means you are giving remember, every signal is made up of a bunch of rotating sticks. You're taking each of those sticks and you're giving it some phase shift. You're moving the starting point from the horizontal to some other phi. And that phi is proportional to k, how much you've moved the time domain signal, but it's also proportional to m, which means the stick that is moving slower, you're moving it a little bit, the phase shift is smaller. The stick that is moving faster, you're giving it a bigger phase shift. Okay. Let's look at an analogy. Let's look at an example. Yeah, here's an example. And I think this is the math behind it. This page is the math behind it. If I do this example, this math will be clear, but I want you to go back and look at this math because it should be absolutely clear. Okay. So let's look at this example. Cos 2 pi f1 NTS plus cos 2 pi 2 f1 NTS. Let's say this is the signal. Right? Guys, what are the rotational building blocks for this signal? Someone? A stick that is rotating at? Tell me. What sticks do you need? What frequency sticks do you need to make up this whole signal? F1.
F1 and 2F1.
Fn minus 1.
F2.
2F1, F2, 2F1. Yeah, F2 is 2F1, right? And Fn minus 2. Correct. Right? You need 4 sticks.
Yeah.
Very good. Okay, good. So look, at time t0, you have 2 sticks starting over here and 2 sticks starting over here, which gives you x0. Do you agree? You have 4 sticks, but all of them are actually starting at the same position. Right? And these are half, 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 half. Oh, well, these are actually 1/4, 1/4, 1/4, 1/4. Each of the sticks. Do you agree? Hey, no. Sorry. These are half, half. Half, 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 half. Because at x0, this is going to be 1 plus 1, which is 2. Agree? Cos 0 plus cos 0 is 1 plus 1. Questions? Okay. Now, look at the first time step. The first time step, one stick goes theta, the other stick goes n minus 1 theta. On the fast one stick goes 2 theta, the other stick goes n minus 1 times that theta, but that theta is 2 theta, so it goes 2 theta in the negative direction.
Does that mean the higher frequencies are slower the greater the original frequency is?
The higher frequency?
If since 2F1 is greater than F1, right? Does that mean that its inverse is technically slower than the inverse of F1?
No. It just means that. Oh,
isn't it trap?
Guys, someone tell me what did this stick do to come to 2 theta, to come to negative 2 theta? This stick spun n minus 1 theta to get to negative theta.
Yeah.
What did this stick do to get to negative 2 theta?
I mean, it's spun the same way to reach there, right?
But then it would have reached negative 1 theta.
No, I mean, but not the same rate. I was.
Someone tell me the word I'm looking
You
for.
say it spun 2 times?
2 times.
Oh, okay.
Because it's spinning twice as fast, right?
Yeah, no, I remember now.
Right. So it spun. And now it stopped at negative 2 theta. Right? See, this is how these are the building blocks. Very good. So similarly, so this time at time t1, you add this and this up, you will get your x1. Next time, this stick spins 1 step, becomes 2 theta. This stick spins full circle, becomes negative 2 theta. This stick spins 1 circle, 1 time step, becomes 4 theta because it's spinning double as fast, right? 2 theta becomes 4 theta. And this guy again spins twice, becomes negative 4 theta. This is x2. And so on. This is what gives you this signal. Now you know what XM is. XM is these 4 frequencies. Now it says, this property says, multiply, if you want to shift it, multiply it with e to the power j 2 pi mk. So let's do that. Let's say we want to shift by 1 value. So we want the shifted signal to be this one, right? As opposed to starting at x0, right? That's like shifting by 1. So k is 1. Okay. So now if we want to do that, if we want to find the FFT of this shifted signal, then what should we do? We should take each of the sticks and multiply it with e to the power j 2 pi by n m k, right? But that m would correspond to that particular stick's frequency. Very good. So first stick z1, which is rotating at f1, we multiply that by e to the power j 2 pi by n, m equals 1, k equals 1. The n-1th frequency stick, we multiply that with m equals n-1, but k still remains 1. Does that make sense? Right? Because we said mk, so m is basically a function of what frequency stick we are multiplying. Similarly, z2, you multiplied by m equals 2, k equals 1, because k is the one sample shift that you want. mn-2, k equals 1. So you've taken each stick and you've given that that phase shift. That phase shift is proportional to the frequency of the stick and proportional to the number of samples that you want to shift. That number of samples k is 1. So k remains 1 for all of those sticks, and only the m changes for each of the sticks. Now look what happens. Now let's do exactly the same thing as we did here on these. Very good. So at time t0, this stick is z1 e to the power j 2 pi by n in times this. z1 was this one, right? But you've multiplied this with m equals 1 and k equals 1. That gives you this theta shift. Right? This one, Zn-1 at time t0 was also at this initial step. But you've given this an mn-1 times 2 pi by n. 2 pi by n is theta. 2 pi by n is theta. So you've given it an n minus 1 times theta phase shift, which is you've brought it from here to here. So in the first step, instead of this, you've made it this. And look at the faster one, m2, m equals 2, so twice 2 pi by n, so that is twice theta. And n minus 2 times theta, that is exactly 2 theta and minus 2 theta. Now tell me, if you add these two up, what value will you get? What should this value be?
X1.
X1. Why? Well, look at this X1. Right? This is exactly the same as this, but this happened at time t0 because you shifted the sticks by some values, making it look like what happened to the first case in the second time step, or at t1. So this becomes X1. You keep doing the same thing, this will become X2, so on. Haha, you've shifted. This is k equals 1 sample shift of xn. And you achieve that by exactly doing xm times e to the power j 2 pi by n m k.
I have a quick question. So
Yes.
what would be the value for Tn, the last one? Because we are
Correct.
shifting everything by one.
Correct. This is a repeating cycle. That's a very good question. This is a repeating cycle. So the last one would bring you back to this one. It's a cyclic one.
Okay, makes sense. Thank you.
Yes. Okay. And guys, this one, this whole thing, you can do exactly mathematically. You can say, look, this is my signal xn, and a shifted, one sample shifted version of my signal is basically x1, x2, all the way till xn. And now you can apply the same equations that we did in the past. I want you to do this at home, where we say, recall fz is nothing but x. So x0 is nothing but this vector times this vector. We write that out. And if you write out the whole thing, you will again see what we saw visually over here in this page. You'll see this mathematically over here. Let me just fill this in, and I want you to look at this at home. Oops, one second. So on, and it becomes, sorry, yeah, that's okay. Oh no, sorry. I want you to look at this at home because I want to kind of finish up with Nyquist sampling today, and that way we'll finish up with DSP. Okay, so those were the three properties. Okay, last one is Nyquist sampling, and again, something that comes up all the time. And if you know this well, I think you can check out and drop off. If you don't, maybe we can completely have clarity. Okay, good. Let's do this quickly. Say you are given the following discrete samples. These samples, I give you these samples, and I say, can you reconstruct the analog signal from which I got these samples? Right? And let's say these samples actually are 0, sine theta, sine 2 theta, sine 3 theta. It matches the values of sine. Someone who's new to signal processing will say, oh, this is easy. The original signal must be sine. Right? Isn't that tempting to say? Let's also give some notations here. Let's say this is Ts. Let's also say this time is 1 by 10 seconds. Right? So we can say that frequency f0 of this signal, which is a sine signal, that frequency is nothing but 10 hertz. Why 10 hertz? Why 10 hertz? Guys, why 10 hertz?
One cycle is 1/10 of a second.
One cycle is 1 by 10 seconds, so therefore this has to be 10 hertz, right? So one easy answer is, oh, the analog signal from which you got the sample, right, is sine 2 pi f0 nts, where f0 equals 10 hertz. Okay, aliens are sending you a signal. You work at NASA. Some engineer sampled the signal, came to you and said, hey, look, this is the samples that I got. What signal is the alien sending? And your first gut reaction is, okay, this is not hard. This must be sine 2 pi f0, sine 2 pi f0 nts, f0 is 10 hertz. Question is aliens really sending that signal? Okay, is the analog signal really that signal? Okay. So then the question is, but is this the only signal that fits these values? You see what I mean? Right? Can there be other analog signals that when you sample, you actually looks like it's like a sine. This is in the shape of the sine. Okay. So now here is what I want you to observe. Observe that sine 2 pi f0 nts plus 2 pi m also fits the same samples so long as m is an integer. Tell me if that makes sense. Mathematically, this is true, right? Whatever the values you get over here, if that fits this signal, you're fitting, if it fits this signal, it should also fit this signal as long as m is an integer. Why? Oh, because sine of theta and sine of theta plus 2 pi and sine of theta plus 4 pi and sine of theta plus 6 pi or sine of theta minus 2 pi, they're all the same. Right? So these we are trying to fit some analog signal to the sample, and different shifts, phase shift to that signal will also fit those samples. Now I can write this as, I can say that means sine 2 pi f0 plus m by n ts, sorry, m by n TS, NTS also fits the values. I am rewriting this by taking 2 pi out, and I'm also taking NTS out. So this means 2 pi F0 NTS plus 2 pi M by NTS. NTS cancels 2 pi M. Okay. All I'm saying now is,
what is the N here?
oh, N is the Xn, right? It is Xn. N is the sample number. N is the sample number that you get. So Xn, no, let me not write it there. Xn equals sine 2 pi F0 N TS.
That's
X of N is 0. When N is 0, X0 is 0. X1 is sine 2 pi F0 1 times TS. Sine X2 is N becomes 2 and so on.
Yeah, that's clear. Like N times TS is T here.
Right. So this is X1. This is X2. This is X3. This is X0. So what is your question now?
I think it's clear now.
Okay, good. Okay. So
isn't this digital signal then?
can you speak up a little louder? Sorry.
Can you hear me? It says, isn't we say that this is an analog signal? Wouldn't the way it's written, NTS, wouldn't that be a digital signal?
Okay, no. Imagine I'm saying that there is some analog signal when you sample it. This signal which has this frequency, right? And if you sample that at n time instants, it'll give you these values.
Okay, I think I get that part. I just meant like that where it says like therefore analog signal equals. Wouldn't the way that's written up there? Wouldn't that be a digital signal like sine of 2 pi f?
Let me take that away. Okay, how about that? Okay.
Sorry. Yeah. Okay. Yeah, that makes sense. Okay, I was just like wondering if. Okay, thanks.
So yeah, actually now it's precise in the sense that if this is the analog signal, then this should be the digital signal.
Right.
So
Okay.
the analog part, like the TS, should be changed to T as well.
Right, T. You're actually, that's right too. Yes.
Okay, thanks. Sorry, that was
Perfect.
yeah.
Perfect.
That makes sense.
Yes. Okay. So all I'm saying right now is this signal should fit all these digital values, discrete values, right? Because I have not done anything wrong till now. Okay, good. Now, choosing M as a multiple of N, I can choose M. If you choose M as a multiple of N, that means M by N equals K, where K is also an integer. Then we have sine of 2 pi F0 plus K times 1 by TS, NTS, also fits the values. Right? There exists some M for which this signal will completely, when you sample this signal, you will get exactly these samples. Very good. Now look, this signal is nothing but sine 2 pi F0 plus, what is 1 by TS? 1 by TS is nothing but Fs, which is your sampling frequency. So it's F0 plus K Fs times NTS, where Fs is your sampling frequency. This is now tricky. Why is it that tricky? Because this means that there are many other frequencies separated by KFS from the core frequency F0 fits the given set of points. Guys, does that make sense? I started by saying if this basic signal sine 2 pi F0 fits the samples, then sine 2 pi F0 plus 2 pi M will also fit the sample. You have to agree. Now I massage that signal, that part plus 2 pi M, in a way that if I pick the right value of M, then this becomes sine 2 pi F0 plus KFS times NTS. And then this blue part is the effective frequency. So all these frequencies should also fit the signal. That means you can no longer say that what the aliens were sending you only had F0, because F0 plus KFS also fits. Okay, so here is the visualization of that. You had those samples, and the first thing you could say is, look, this sine F0 fits the samples. But we are now realizing that F0 plus KFS also fits. So that means there can be another frequency which is also sine, which might be F0 plus 1fs or F0 plus 2fs or F0 plus 5fs or F0 minus 3fs. K can be -2. That also fits the samples. If you take the samples at separation of time Ts, for this blue signal, all those samples will also look like a sine wave. And there are an infinite number of them because K can go from -infinity to +infinity. Oh, that means just because we have sampled and we see a sine shape doesn't mean the aliens are sending us a sine 10 hertz sine signal. There can be many other signals, many other frequencies. Okay. So this is F0, this is F0 plus KFS. These are called aliased frequencies. It's as if in this apparent F0, there are hidden many other frequencies or many other signals, which when we sample, it gives us some other shape. Right? Just because you've sampled and you see the shape of the samples, just because that looks like a 10 hertz, it doesn't mean that the underlying signal has only 10 hertz. Underlying signal could have 70 hertz, but when you sample that particular signal in this manner, it might look like a 10 hertz signal. That is, so these are called alias frequencies. That is F0 plus KFS are aliases of F0 for all values of K. Okay, what that essentially means is, even though you see to the eye, it seems like F0 is the signal present, is the signal that aliens are sending to you based on the shape of the samples. Actually, F0 plus Fs might also be present. F0 plus 2Fs might also be present. F0 plus very high Fs KFS might also be present. F0 minus Fs might be present. F0 minus 2Fs might be present, and so on. Many, many, many frequencies can be present in your digitally sampled signal. Don't get deceived by the shape of the digital samples that you've got. Guys, is that clear? Very good. Now also observe that higher the sampling frequency, greater is the separation between the aliased frequencies. Does that make sense? If you make Fs greater, if you make, suppose your F0 was 10 hertz, and now you're sampling at 100 hertz. so that the next frequency that will alias is 110 hertz. The next frequency that will alias is 210 hertz, right? But if you make your sampling frequency 1000, then if you have a 10 hertz signal, the first frequency that is aliasing is 1010 hertz. So as your FS increases, the frequency that will alias is also moving further and further away from your deceived or base frequency or F0 frequency. Okay. So now let's look at a signal. Let's say that cos signal which had F1 and minus F1. These are the two signals that, let's say, are present in a cos signal. But Fs minus F1, sorry. Yeah, guys, why don't you tell me which signal will alias to F1 and minus F1? If I'm sampling at Fs?
Fs plus F1.
Fs plus F1 is over here. That will alias over here. Keep going. What else?
Negative F1 minus Fs.
Here. That will alias to this one. What else?
Negative F1 plus Fs, maybe?
Negative F1 plus Fs, and that will come here. That will alias to here. Let me draw that.
Negative F1.
And F1 minus Fs, which will be here.
Oh, yeah.
That will have alias to here. Do you see the aliases? Right? For every F1, F1 plus Fs, F1 minus Fs, both are aliasing. For minus F1 minus Fs, minus F1 plus Fs, both are aliasing. Okay. So if I sample a signal at Fs and therefore get to see frequency components Fs by n, 2Fs by n, 3Fs by n, and so on, actually, each of these frequency components could have aliased frequencies from other frequency components contained in the signal. Right?
I had a quick question.
Yes.
In the previous page, is K only an integer value or?
K is only integer values, right? Because we chose m by m in a way, such that m by n is k.
Okay, because okay, it just said like for all values of k, so I was just confused. Okay.
Right. I mean, basically, I choose m as some multiple of n, so I will get all values of k. If I choose m as 2n, I'll get k as 2. If I choose m as 3n, I'll get k as 3.
Is k necessary to be an integer, or it's not?
It has to be an integer, yeah. Yes.
Why would that be a case? Like m is necessary to be an integer, but it seems it's not k here. Like m is an integer.
Because
like
you want this NTS and this NTS to cancel. Right?
Mm-hmm. But even if like k is not an integer, but m is an integer, like these two parts will cancel as well.
Even if k is not an integer, then wait. If I take 2 pi m in NTS, you have a point. Okay, let me think of this and come back. I'll come back and answer you.
Okay, okay. Because I just feel it's
not being able to think of the reason. Huh?
I just feel it's like some simple math. Like,
yeah. It's not coming to me, but there is definitely a reason that k has to be an integer.
Okay.
Yeah. Okay, so assuming that, so that means there are many frequencies that are aliasing into my F1, right? So the question is, now suppose you're supposed to figure out what signals are the aliens sending. What can you do? Right? You have sampled the signal and you saw F1 and minus F1. You cannot say that this signal is cos 2 pi F1 NTS or 2 pi F1 T. You cannot say that. We know that. We cannot say that because there could be other signals, other frequencies. Instead of F1, or rather say F0, instead of F0, there could be F0 plus Fs, there could be F0 plus 2Fs, F0 minus Fs, all kinds of signals can be present. So you cannot say for sure this is the signal that aliens are sending. Right? So what can you do? Actually, the answer is you cannot do anything. Okay. So what's the best you can do? The best you can do is, suppose I tell you that the aliens can send a max frequency of F max. This is the max they can send. Or I tell you the bandwidth of the signal. Right? This is the maximum frequency. Which means now you say that, okay, look, the aliens must be sending some frequencies around here, but it cannot be more than F max or less than minus F max, because that's the bandwidth. Remember that plus minus F max. Okay. So now suppose you know, let me write this here. Suppose you know the max frequency of signal equals F max. And this is bandwidth. So then what you can do is, first easy thing you can do is you say, look, if there is no frequency beyond F max and less than minus F max, you filter out all frequencies that are greater than F max and less than minus F max. You basically say, I'll filter all these out when I receive the signal. Right? I can do that immediately. And if I filter those out at the analog, while receiving the analog signal itself, I know that the only frequencies that I have must be within F max and minus F max. So this filter is called an anti-aliasing filter. And it's an analog filter. Okay? So this is the anti-aliasing filter. Now, is that enough?
I don't think so, right? Can't you get aliasing within that bandwidth?
Exactly, exactly. That's not enough, right? Why? Now imagine your sampling frequency Fs is less than or equal to F max, right? So that means frequencies that are between F max, minus F max and F max will alias onto F max. How? Imagine this is your Fs. if this is your Fs, then Fmax minus Fs is this value. This is Fmax minus Fs. Right? If this is Fs, you subtract that from Fmax, that will give you this. So you will have, so some signal that is over here will alias into your Fmax. Right? So if you get that alien sample and you see some frequency at Fmax, it actually may not be Fmax. It might actually be Fmax minus Fs because you're sampling at Fs. So if your Fs is less than Fmax, that won't work. What if your Fs is greater than Fmax? Suppose your Fs is over here. Will that work? Or suppose, sorry, your Fs is over here. This is your Fs. Will that work? Even that won't work. Why? Because if this is your Fs, then Fmax minus Fs is here. And that signal will alias into Fmax. So the only way to prevent any frequency from minus Fmax to Fmax be getting aliased into your signal is when Fmax minus Fs is less than minus of Fmax. Does that make sense? In other words, any of your internal frequencies, any of these frequencies should not alias into your Fmax. Right? You don't want any of these frequencies to alias into Fmax. And the only way you can do that is if you increase Fs enough, you're basically pushing the aliasing frequencies away from your Fmax. Right? So you make your Fmax minus Fs less than minus Fmax, this, which means if you make your Fmax minus Fs over here, this is Fmax minus Fs. Right? That means all these frequencies are anyway getting cancelled out by the anti-aliasing filter. So nothing, so no frequency from inside your bandwidth will affect other frequencies inside your bandwidth. And this tells you that Fmax did I do this right? This tells you that Fs should be greater than 2 Fmax. Okay. So Fs is greater than 2 Fmax, and that's called the Nyquist sampling rate, where the sampling rate is greater than twice bandwidth. Okay, I think we are done. So now this is the signal processing pipeline. You get a signal. You first use your anti-aliasing filter. Right, you filter out everything more than bandwidth, right? Because any frequencies over there, you don't want to alias. Then you do Nyquist sampling. This is your analog signal, you Nyquist sample. You do anti-aliasing filter in the analog domain. Then you do Nyquist sampling. If the max frequency is 20 kilohertz, you Nyquist sample at greater than 40 kilohertz. You get XN, which is a digital signal. Now this digital signal, you take an endpoint FFT. And once you take the FFT, now you visualize the signal and you see, haha, if it's a real signal, then it's symmetric around 0, right? And it may or may not have phase depending on what that signal looks like.
So you turn it into an FFT to visualize it?
Yeah, I mean, you can do many other things with that, right? You can do all kinds of computation on the FFT.
Mm-hmm. Okay.
Right? So for example, if you have a phone, the phone has an accelerometer. The phone accelerometer gives you some time domain signal. You take the FFT and you see that the frequency that is most dominant, right, is like 3 Hertz. And then you know, that 3 Hertz corresponds to the human walking. Right? Because human walk is typically 3 cycles per second around roughly. Right? So now, if you look at the time domain signal, there may be many other things happening. The person might be playing with the phone and typing on the phone. From the time domain signal, you won't be able to see which is the bounce of the walk. But once you look at it in the frequency domain, you'll see some high frequency signals, which is the person typing on the phone. But you'll also see a 3 Hertz, which is the person walking. So by looking at things from the frequency domain, you can get certain views, right? Suppose your car is making some weird sound and you don't know what is happening. From the sound, you cannot tell. So you take that sound and you take an FFT, and then you see that that FFT, there's a high signal component at maybe 20 Hertz or maybe 200 Hertz. And then you know that, oh, the piston of your car pumps at 200 Hertz. And that means there's some problem with the piston. Because from the frequency domain, you see that 200 Hertz has that high sound. If you look at the time domain signal, you won't be able to say anything. You won't be able to diagnose that that sound is coming because of a piston problem. Right? So moving things to the frequency domain gives you an extra kind of analysis, insight into what is happening inside the signals. Okay. Okay. Done with math. It's way too late. But next time onwards, we are getting into applications. So there won't be this inertia to make sure you understand every bit of it. Many of the applications are easier to understand once you understand the foundation math. Okay. Questions, guys?
Yes, sir, I have a quick question.
Yeah.
Could you scroll up to that drawing you had of the 2 signals for the aliasing part?
This one?
No, a little up. One more. Yeah.
Yeah.
So you're saying that the second signal you drew, when we sampled it at a certain rate, we got the same signal?
Correct. We got the shape. This blue signal, when you sample it at every TS.
Yeah, we got the same. Okay.
We got the shape as this shape.
Gotcha. And then my last thing is above you added 2 signals. I was wondering how that actually worked.
Which one? Which one?
Or above. More above you, yeah, right above this, I think. Yeah. So in this, what exactly are you adding? Because I see that the top and the bottom have like those, like the 2 signals cancel each other out. But why are you adding 2 different signals?
Oh, because and then this X that I have is made up of cos 2 pi F1 NTS and cos 2 pi 2 F1 NTS.
Yeah. Okay.
So one has a frequency F1, the other has a frequency 2 F1.
Mm-hmm.
So, you know, when we have a frequency F1, we need 2 sticks. One at F1 and one at Fn minus 1.
Mm-hmm.
For 2F1 also, we need 2 sticks, one spinning at 2F1 and the other spinning at 2 Fn minus 1.
Yeah.
So we need 4 sticks altogether. 4 spinning sticks.
For both.
Yeah. And now what is your question?
So yeah, well, you're adding in the first one, you have Z1 e to the J2 pi. So that's the cosine F1.
Right.
And the second part is the cosine 2F1.
Correct. This is the cosine F1. This is the cosine 2F1. But remember, we have to multiply by mk. And this m, even for cosine F1, we have one m as 1 and the other m as n minus 1.
Mm-hmm.
And for cosine 2F1, we have one M as 2 and the other M as...
Yeah. Wait, so are you multiplying by the XM?
Say that again.
All right. Not the multiplying part. What is that XM e to the power j, like the red writing to the right? What does that represent?
This one?
Yeah.
This one, we are saying that the third property of FFT says that to get the FFT of a shifted signal, you take the FFT of the unshifted signal and you multiply it with a phase shift. Oh, sorry, wait, yeah. Sorry, there was an internet lag. To get the FFT of the shifted signal, you take the FFT of the unshifted signal and then multiply it.
Yeah, and then you multiply. Okay. Oh, so you're just showing that that's what, okay.
I'm just showing that you take these unshifted signals FFT and you multiply them with a phase shift, you will get the FFT of the shifted signal because look, this is the shifted signal.
Okay. Wait, so that's what, so then shouldn't all this be added together or no?
Which two? Yeah, when you add them together, that is like you get back to the time domain.
Yeah, so you have to, but shouldn't there be 4 things you should be adding? So, so this whole thing.
I added 4 things. 1, 2, 3, 4.
Yeah, I'm talking about the equations you wrote above, the one you have.
Here.
Are you saying that we think all 4 to represent one?
Sure. I can put a plus over here.
Okay.
Yeah. Right.
Okay.
Yeah. Perfect. Why don't I do this? I'll do this one. This plus this. Is that better? Right? These are
these
are the 2 sticks for F1. These are the 2 sticks for 2F1. And then you add the
Gotcha. And then I'm assuming Z1, yeah. And then Z1, Z2 are all magnitudes in that domain, right?
Z1, Z2 are the original. Z1 is this stick. Z1 is this stick rotating.
Yeah, got it.
Cn minus 1 is this stick rotating.
Got it. Okay, thanks.
Okay, I'll stop recording over here.